Oi, machine learning for predicting chaotic systems. This is a cool paper. Usually I do deep learning stuff. This is regular ML and a little bit of deep learning in there, but more so, it's a lesson to be learned for all of us who are very high on our universal approximation theorem stuff, that some systems just really cannot be approximated. All right, so if you're curious to find out about that, stick around. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. Disclaimer. So, in case you weren't already aware, right? Chaotic systems, I know my channel is more about AI stuff, and chaotic systems are not very touching AI. Generally, this paper is very much an intro for most people to the field, I would assume. But they are systems characterized by their sensitive dependence on initial conditions, making them notoriously difficult to predict. So, the nature of these systems is such that if you were to take one of the input variables, for example, like weather is a big one. If I show you all this, for example, is called the Lorenz curve. Uh, I forget the specifics of how it was simulated, but basically there's three very simple variables in like a weather simulation model that's a certain area of the climate weather. It's not all climate weather area stuff, but let's say three variables that are, for example, humidity, temperature, and I don't know, wind speed maybe or something, right? Some area, some weather variables, right? In this system, it is the case that you can start off with an initial point. That would be, this would be the initial point that on the bottom right there. And then you hit go on the simulation, which is just a partial differential equation setup. And you will see it behave in a certain way where variables go up and down over time and they move. And first thing is, you notice when plotting them in three dimensions, wait a minute, they move in a really weird pattern. They kind of have these attractor states, that's the center of the circles, that they kind of gravitate around, right? And they unpredictably at random times jump from one of those circles to the other one, from one attractor state to the other one, right? And I say unpredictably, I mean unpredictably. The important part here is that sensitiveness to initial conditions, right? Meaning, if we were to take our initial point, that point down the bottom right there, and we were to rerun the simulation, but change one of our variables, let's say humidity, and change it by 0.000000001. Very, very tiny little edit to the initial condition, right? It would start off, the beginning would act a little bit the same. It would go along that same initial curve, but after a given time period, depending on the system, it will, like, which you kind of define as the initial short-term period, it will sort of diverge. Even though that initial starting condition was just so close, you would imagine nothing would be any different. That little tiny difference, the 0.00001, has a kind of feedback loop effect where after a while it completely diverges. It goes in an entirely different new pattern. It chooses a different time to jump from one circle to the other. It has a wholly different sized orbit kind of thing. The behavior becomes is by definition of these systems, due to this kind of feedback loop they have inside of them, massively unpredictable. If you've ever heard of the butterfly effect, that was a big thing in like 2015 maybe or something, people talking about it. It's the idea that a butterfly flapping its wings on in America could cause a hurricane in Japan. I don't know if they have hurricanes, but whatever. Could cause a hurricane in Japan. And what it means by that is a butterfly's flapping of its wings is the equivalent of our 0.0000001 initial condition change. That any given little piece of the system like that, any tiny little change of the system, can have monstrous, unpredictable effects down the line, completely changing the behavior of the system, as if it had not happened, right? And it's actually true that this is kind of like a law of the way these systems work, is that no matter how small of an edit you make, add as many zeros before the one as you would like to, this will still be the case. Eventually, you will still see the behaviors of two simulations that are like just 0.00 whatever one off of each other. They will diverge completely eventually, and usually relatively soon. Like it's not it's the reason why we can have pretty good weather predictions on the next 12 hours. And when you hit like 24, 48 hours, it's like, oh, the specifics of like what time of day it's going to rain get kind of iffy. When you hit like a week or two from now, just totally useless. Like with our predictions are totally useless because it is the case that even if we had a measurement device, like a temperature, humidity, whatever measurement device, every single square inch surrounding the planets, like every single from ground height up to Mount Everest height, every single square in the cloud and stratosphere, and every single inch movement, there was another device that was recording. Even if we had data at that level of granularity, you still would not be able to predict the 2 weeks from now weather any better than you currently can predict it because it is so sensitive to initial conditions. You would have to not just do inch apart, you have to say, well, no, now we need millimeter apart. No, actually, we need micrometer apart. It would get all the way down to effectively Planck distance, like quantum level type stuff. Is the sensitivity to initial conditions is wildly insane and consistent, and that these systems just don't care, uh, or just do care about the slightest little discrepancy, and it will completely change their behavior, right? Making them very hard to predict. Now, when I say that, I'm not trying to like don't jump to climate change or anything. Don't overestimate how much you understand so far. It has like a tiered effect and it applies in some places, doesn't apply in others. You have to actually have a chaotic system for it to apply. Unfortunately, the weather example gets brought up frequently because back in the um, 19, I want to say 80s maybe when it was discovered, the Lorenz guy, who I don't know if he founded it, but the Santa Fe Institute was close after him. They were the big people around chaos theory. Uh, Lorenz's initial experiment where he found this result, where he found this type of system, was around the early days of computers, and he was doing a simulation, and he thought that he had messed up a simulation run, or like he thought like something had gone wrong, and he realized all he did was edit like a decimal point by a very tiny piece, and he started like looking into it, and he discovered this stuff. But yeah, basically, like I said again, do not overestimate or assume what systems are chaotic and which ones are not. Don't just jump to thinking like climate change isn't real or whatever. I haven't looked into it, but as far as I'm aware, my impression is that the long-term trend in climate, it does not count as a chaotic system. But anyways, I digress. That was like the background info as to this paper. And the question in this paper is, how can we, or can we at all, use machine learning models to predict chaotic systems? And we'll find the answer to this soon, and it will have implications for how you think about AGI and the future of AI and all this stuff, right? Now, traditional approaches to modeling chaotic systems involve using domain knowledge, meaning that we know enough about the weather, for example, to actually know what the equation should be to make a model of the system that we can then use for simulations. However, that approach is kind of annoying because it requires that you actually understand said system, right? Which is not always the case. So, in more recent years with machine learning, there have been attempts to see if we can do system agnostic, meaning can we take a machine learning model that does not know the parameters of the equations of the system ahead of time, aka is not a physics informed neural network or anything like that. It's just a regular system equation agnostic model. And can we use this data driven approach to emergently learn the actual equation, or at least a system that simulates it, and how accurate can we get? And now, the issue is that, unlike for natural language processing, for example, right now there is no consensus in the literature on which method should be preferred, which is an immediate red flag to you. Like the fact that like people have proposed dozens of methods that try and do a machine learning or even deep learning style model to simulate chaotic systems, there is still no clear consensus. And the paper today is explaining and is looking into which one should be the consensus, if any. Now, a big reason there's no consensus is because we really lack robustness of comparisons. Given that these systems are so sensitive to randomness, you really need to go well out of your way to comparing everything on equal terms in a way that is not the case in most fields of science. Don't get me wrong, like it's great in science when you can like compare on equal terms and get like controlled trials or whatever it is, or good data kind of stuff. But in chaotic systems, it is especially important that you literally use the same computer, the same GPU for your simulations, because even the floating point number calculation differences, or the GP or the rand, whatever, there's some randomness in there, like stuff like that, even just like tiny little errors or whatever it is, the slightest bit of difference in how something is done ruins the whole comparison, basically. You need absolutely perfect on the same machine with the same random number generator seed for everything. It's like a whole thing, right? And this paper today does that effectively. It tests out a bunch of different methods and sees which ones, like on the same computer, and tries to see which ones are better. I won't get too deep into it, but a big contribution of this paper is a new data set that is not huge in quantity. I think a previous one I looked at has like 133 different data sets in it, where this one has like 3 or 4 of them. But quality wise, it is really everything you could ask for in terms of noisy versus not noisy, all this stuff, and the actual number of repetitions per actual data stream type, and the total amount of data per time series. It's a whole order of magnitude better. Now, what are these comparisons? Basically, given past observations of the time series data on a given time interval, which is your training period, and then the true current state of the system, predict the future states at a given selected time is all it's being asked to do. Is what is your prediction accuracy in terms of time series continuous data? Of course, they have to normalize for different scales of data and everything, given like what order of magnitude are you even on for all this stuff. But basically, think of it as just mean absolute percent error. Not a big deal. I did want to highlight, though, a new contribution of theirs, which is the cumulative maximum error metric, which combines the advantages of the two more common metrics in the fields. And think of the cumulative thing, it's cumulative error over many time periods, right? Now, what are the actual models, methods, machine learning techniques that we are testing, right? So these first few, constem, const-L, analog, I'm not going to actually detail specific ones in the future. I just wanted to say like we're for each category, there's multiple in the category, but this first category can be treated as like trivial baselines because no fitting or learning is required. They're basically, my impression anyways, is just moving average style predictions, like very, very simple stuff. Then the next group is called propagators. These are effectively just regression tasks on the data. And then once you have that regression done, you have to recursively apply the equation you get because these systems, that dependence on previous conditions, they are themselves recursive in how they work. You do a regression to get an equation that you can then use recursively on whatever input data you have to see what the future time step is, where each recursive use is itself a movement forward in time by one step. Next category are these solution smoothers that work in 3 steps. First, they do a regression. Then, kind of confusing, they view that data as observations and use a second regression estimator to obtain a specific function. And finally, they solve for the actual ordinary differential equation on the given time interval with those initial conditions. So this is more of an approach designed to take advantage of the knowledge that they are ordinary differential equations. Ordinal, ordinary, I'm blanking. I haven't taken linear algebra in so long. It's actually embarrassing. A point about hyperparameter tuning, I'm not going to get too deep into it or anything, but given that those different categories of models are hugely different in complexity, those last 2 categories, the regression and the smoother whatevers, can actually, you can put in a full-on deep learning model inside there to use as your regressor. These models, depending on what you do with them, have wildly different requirements in terms of their actual hyperparameter tuning, meaning like the costs are so different. And this paper is really just focusing on what works accuracy wise end of day. It is not so much focusing on actual training cost, hyperparameter tuning required, any of that stuff. So that is a whole extra issue. But again, we'll see later, the results are more important than the actual specifics of the computational cost. Now for the results. Here's the big finding that we in deep learning are not used to hearing. In all settings with a constant time step, meaning some of the data sets have time steps that, like it's, oh, you have a data point at day 1, data point at day 2, data point at day 5, data point at day 12, data point at day 13, like random time steps, as opposed to constant time step being every single day. In any setting that has a constant timestamp, the best methods are these simple ones with very low computational cost. In contrast, the complex high-end learning methods perform very poorly. And the question here, the critique they're making is like, yes, they perform poorly, but we should think about this fact that like chaotic systems are usually anyways described as low dimensional systems. So it might just be the case, and that's true of the data we have here today. the data set they're training on. So it could be the case that it's just because we're using low dimensional data, and that for low dimensions, there's no use in overcomplicating things with big models that require much more training data, when in reality, the simple models seem to actually just not only be more computationally efficient, but just straight up work better. Now, they have four combinations of making the task difficult. First is, are the time steps consistent or random? And do we have the actual clean data or noisy observations, right? When you do random time steps and noisy observations, which is a pretty realistic real world scenario, consistent timestamps are also realistic, but the most like that's either one can be happening based off just what your data source is like. Does your data source actually collect consistent data or not? But the noisy observations thing, that is big. And when you combine both of those two things, it seems to make the learning task so difficult that only very few methods are able to beat the baseline, which is equivalent to saying are like able to beat like random guessing effectively would be the baseline. Here are those pretty graphs I mentioned over in 2D. Just wanted to show them. They do always look cool. I really love these things. For a while, I had one as my desktop background back in, I want to say, sophomore year of college, maybe. And here are some of these results graphs where they basically on the x-axis have the methods ranked, I believe, by how well they did. And you have to just kind of look them up to see which category method it lies into. But on the bottom left here, we have the best performant ones, top right, worst ones. Think of it as accuracy. It's not accuracy, it's the whole cumulative thing that they made, but close enough, right? And this is for constant time steps with no added noise, so the actual correct data of the system. Then when we add in noise, look at that. The accuracy really gets, not accuracy, sorry, loss or whatever. But anyways, higher is worse, lower is better, sorry. It gets significantly worse when you add noise. And it also evens the playing field a bit, given that this graph, this trend line here, not trend line, but this would be a less steep of a curve. Here we have random time steps, no noise, which does a bit better. Some of these models do better in than consistent time step with noise. When you by the time you hit random time step with noise, really just these things do not work effectively. Not very good. You might as well at that point just not bother estimating the actual system and just say, oh, it's up to the gods. Like, who cares? All right, now I know that was a bit out of distribution for us on this AI channel. Like, it is talking machine learning, but it's very much like we don't usually do chaotic systems here. I'm more of a language person. The lesson I wanted to teach though with this was just that uh, even this idea of universal function approximators, some functions have implicit unpredictability in them is part of the issue, right? I don't think that we'll have some people are like out here in my comments going like, oh, it'll be a godlike being. It's not. It will, if you want to define God as like every single possible task being finished, I really don't think that's the case. At the end of the day, like, there are limitations in physics as to how well you can make predictions on certain systems, very common systems. We discussed weather today. The economy is definitely a big chaotic system. Large parts of it, anyways, not all parts, but most of it. Another example would be look up the three body problem on YouTube. That's a what's it called? A planet orbiting problem. But anyways, the idea that like transformers or whatever it is can actually learn literally everything is pretty silly. We know it's not true. This is an example of a class of problems that are probably just not learnable, period, that are just fundamental, like, not they are deterministic, don't be wrong, they are deterministic. They're not like random in that sense, but they are deterministic and unpredictable, which is a combination people don't usually think of. People usually think of like randomness meaning unpredictable, but actually this case is a system that is deterministic and unpredictable. So it is a kind of ceiling on the capabilities of AI that we will not, probably not. Like, my impression is that, like, I haven't done it like forever. I haven't like read through the chaotic systems literature in so long. My impression is like these are full on proofs. Like, you can't get around the reality of the truth of how these systems work. There is no special cure for this. So, anyways, hope y'all enjoyed that and like and picked up on the actual ending lesson of the video. But yeah, I guess skip to the outro. Don't leave yet. If you got this far, you're gonna love this video or this playlist. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.